So we have reached what I think is one of the coolest applications of all of calculus. I think it's one of the most underrated applications of all of calculus. And it's this idea called linear approximations. And before we get into the nitty-gritty technical details of it, I'm just going to give you a baseline intuitive understanding of what on earth it is that we're talking about here. And the way I'm going to do it is I'm going to give you some ridiculous looking function, right, f of x, okay? And I'm going to say, let's pretend that this thing is just some disgusting, natural log of sine of e to the 7x plus x squared, right, over tangent of x, right? It's just some obscene function that I've made up that's really hard to evaluate. And let's say, whatever this thing represents is like money. Let's say, this is the profits that you're going to make based on whatever X is. And so, you're working for some company and your boss comes in one day and says, hey, I need to know, what are the profits over here when X is equal to 40? I need to know exactly what is this value. And you sit there and go, oh man, that's the function I've got to evaluate. This sucks. And then your boss says, oh yeah, while you're at it, not only do I need to know what the y value is when x is equal to 40, I also need when x is 41, when x is 42, when x is 39, 38. I need to know for all of these x's kind of in this interval here. And I need to know for anyone. I could pick 39.6, I could pick 38.2, 47.3, right? I just need to know, and I need them quick. And you would just sit there and go, well, this thing is really hard to compute. And even if you had a computer to do it, right, that computer would take a lot of processing power to evaluate this thing again and again and again and again and again. And so what someone noticed was they said, okay, well, hang on a second. We just talked about this thing called a tangent line. And they're like, yeah, so what? Well, if we take a look at this tangent line, right, this tangent line, Let's pretend that the equation of this tangent line is just y is equal to x minus 30. Okay, let's just say it's x minus 30. We're just making this up here. Well, if I had to then evaluate, what is this point when x is equal to 40, which one of these equations is easier to do that? Should you plug it into the pink one? I mean, technically that's the most accurate. But this tangent line actually looks like it's doing a pretty good job, right? If you zoom in here, the y values of this blue line and the pink line, they look to be almost exactly the same, if not very, very close. And you'd say, boss, no problem. You'd say that y is approximately equal to 10 when x is equal to 30, right? You could give them an answer immediately. And they said, okay, well, how about x is equal to 41? Right? And your boss is expecting this to take a long time because you need to plug it into that. But you have the equation of the tangent line. And you know that even if let's erase some of these tick marks here. But even if you were to move over just a bit to x is equal to 41, right? And you were to go here, right? Sure, if I zoom in on a micro level, the actual y value is up there. And the y value that you're getting from your tangent line is there. But they're so close that for all intents and purposes, unless we have a very, very, very small, room for error, I could just say, oh, well, at x is equal to 41, I can use the equation of the tangent line and say, oh, my y value it's approximately going to be 11, right? That's a pretty reasonable thing to say. Now, the tangent line then, if you kind of believe this, ends up being this really, really powerful tool. And kind of on this interval, you will, maybe from here to say here, you'll notice that if I look at the values of my function kind of on that interval, specifically if I look at the y values, the y values of what my function is are not too far. They're not too far from my guess, from my approximation that I'm getting from my tangent line, right? That they stay relatively close. Now, obviously, if I go too far away, right? If I start asking you, okay, well, what is the what's the y value when x is equal to 63, you know, and your tangent line is kind of going over here and your real y values are all the way up there, yeah, you know, you're going to get some bad answers, right? Because your guess is going to be here, but your real y value is going to be way up there on Mars. And so this is the concept of linear approximations. The idea is that, you know, we can take really complicated functions, and if I know the equation of the tangent line at a particular point, then I can use that tangent line as long as I stay what I'm going to say is like close to whatever point that I drew the tangent line at, what we call is like the center of the tangent line. As long as I stay close to it, then I can use the tangent line to approximate the y values of my function, and I'll more or less be correct. There's going to be like some small little bit of error, but I'm more or less going to be correct. Okay, so let me write down a couple things. So the idea is that the tangent line, okay, the tangent line can approximate, or here I'll say the tangent line at a point, can quote unquote approximate the values of a given function, in this case my pink one, of a given function f of x, so long as we're inputting x values that are like close, x values that are what I'm going to call close, right, to where I drew the line, to where I drew, I'll say, I guess I shouldn't use I. We is the proper math thing, where we drew the tangent line, right? And that's the idea, is that this tangent line, you know, is super nice because it is linear. And what we mean by linear is it's just a straight line. That's what makes this a linear approximation. And, you know, this is kind of like, this is going to be a little bit of a sidebar, but I think it's really cool. You know, if I were to talk about a nonlinear approximation, right? So we said, look, we have this point, and I want to create a linear approximation, which is just this tangent line at that point, and I want to use it to estimate y values at different x values, right? At different points kind of near it. That makes sense. But as I pointed out, right, the further this direction I go and the further that direction I go, the further apart our guesses get, right? So if I start picking x values here, you know, the y value that I'm going to get from the tangent line is down there, but the actual y value is going to be up there. We start to get like a gap between the true answer and our approximation. And so it may beg the question, well, if we have linear approximations, right, this is just the equation of a line, y equals mx plus b, could we have a nonlinear approximation? And it turns out, yeah, you'll learn about that in Calculus 3, this concept, what we call a Taylor series or a Maclaurin series. But just as kind of a heads up, you could imagine that if I were to use a different shape, like say a parabola, right, that I could create a parabola of some sort, right, that does this, and maybe it approximates the function even better for a long period of time. You'll notice that it kind of is closer to my function for a longer period of time than my linear approximation was. And you could just take that concept and run with it. You could say, okay, so that's a quadratic approximation. That's something with an x squared in it. You could also take that idea and run and say, well, maybe we could do something with an x cubed, because a cubic looks something like this, right? A cubic kind of does something like that. And there's a cubic function, and now it's starting to match this given function for even longer than the quadratic. And you can kind of keep going, and the idea is that, you know, if the higher power we make this, right, the longer the polynomial that we use, we're going to start getting a more accurate estimation of the original function. Now that concept's a little bit advanced, and if you'd like to learn more about it, you can check out my multivariable calculus videos where I do talk about Taylor series and the intuition behind it. But the purpose of this video is linear approximations, and hopefully now we have an idea of what the heck it is that we mean when we're talking about it. So I'm just going to give us an example, because I think that's really the best way of doing this, to really kind of to get what's going on. So for example, use the linear approximation. Use the linear approximation of the function y is equal to x squared, centered at x equals 3, to approximate the value of our function when x is equal to 3.1. Okay. Now I am using a simple example, right? I totally know that you could all take this and just plug this into the original function and give me the exact answer. I know that. But we're going to practice using this tool. And I'm going to draw a picture again, because I think that visuals are a really important part of what we're doing here. And so here is our parabola. Y is equal to x squared. Okay. And we are going to create a linear approximation, aka a tangent line, when x is equal to 3. So here is x is equal to 3, which should go all the way up to this point, which hopefully we know is the point 3, 9. And the idea is that if we create a tangent line here, so if we create this tangent line that, more or less, as long as I stay close to this point, right? Or in other words, I don't deviate too far from x is equal to 3, what we call the center of our linear approximation, or the center of our tangent line, aka where we're creating our linear approximation at. As long as I don't ask you to approximate the y values for x's that are super far away, then this green tangent line is going to do a really good job for us at giving us a good guess. So let's just kind of do it in action. What this is basically telling us is we need the tangent line. We need the tangent line at x equals 3. Okay. And so in order to get the tangent line, or rather the equation of any line, we're going to need a point, which we have, right? They gave it to us. Well, technically they didn't give it to us, but we were able to figure out that it's going to be the point 3, 9 from the function. And then the next thing we need is the slope, and we can get the slope of this function using the derivative. So y prime evaluated at the point 3, 9 is what we're looking for. We need the slope here in order to get the slope for our tangent line. And so thankfully, y prime, we remember just very quickly, y prime is equal to 2x. And so y prime evaluated at 3, 9 is going to be 6. And so we just now have the equation of the tangent line, y equals mx plus b. We just need to solve for b, and we will have the equation of our tangent line. So plugging things in, we have 9 for y. We have a slope of 6. We're at the point when x is 3 plus b. So we get 9 is equal to 18 plus b. Or in other words, negative 9 is equal to b. And so that makes the equation of our tangent line, y is equal to 6x minus 9. And so this is our tangent line. And you may see in the textbook, they might call this thing instead of y or f of x, which we might call it, they call it L of x. And why do they call it L of x? They call it L of x because it is the linear approximation of the function y equals x squared. Okay, and I want to specify that this is the tangent line, what we call centered at x equals 3, which basically just means that we made it at this particular point, okay? And so now we're just going to do exactly what they ask us to do in the question. They say approximate the value of our function when x is equal to 3.1. So let's do it really quick. So that means that they're zooming in here and they're saying, hey, I need to know really quick off the bat, what is the value of this function going to be when x is equal to 3.1? And so we can go up, right? If we could just go up from that point and we go up to our tangent line, we can say, okay, I can use this y value. Maybe the real y value is up there, but we're going to use that y value on the tangent line, which means all I need to do is to take this tangent line and plug in x is equal to 3.1. And again, I would rather plug in x equals 3.1 into a linear equation than I would anything that's nonlinear any day of the week if I had to do it in my head. Now, granted, I understand most people will probably use calculators, but, case in point, I don't have to use a calculator to do this one anyways, because I'm going to get y is equal to 6 times 3.1 minus 9. I can't read. Minus 9. Now, 6 times 3.1, I believe, is 18.6 minus 9, which is going to equal, hopefully, 9.6. And this would be our approximation of what y equals x squared is if I were to plug in x is equal to 3.1. Now, I'm going to encourage you really quick to pause the video and pull out your calculator and to do 3.1 times 3.1 and, get what the answer is. If you do it, if you were to check, so maybe off as a side, so how does our approximate or our approximation compare to the actual answer? So to the actual answer. And it turns out that, if we were to figure that out, if we were to do 3.1 squared, we're going to get 9.61. And so what we just found out is that this tangent line, which took us just a couple of seconds to really make, we're only off by 1/100th, right? We're only off by just 0.01 units. And, we're just using the equation of the straight line instead of having to do y equals x squared. And I could use the equation of the straight line for other x values as well. Now, I do want to just make a quick comment before I finish this video in that, I have been mentioning that the further away you go from the center, there's going to be more error, right? You can kind of see it if we zoom in here, right? You can see that the tangent line, pretty quickly for this particular case starts to deviate, right? The y values that I'm going to get versus the actual y values, the gap starts to get pretty big pretty quickly if I start going too far. And there is some math that you can do. There's what we call error analysis. And the idea basically is kind of depending on your application, you can get away with using a tangent line depending on how much error you want to allow into your program. So for instance, if you're in a video game and people are constantly, let's say they have to, shoot a bow and arrow or something, right? There's like a little arrow and it's gonna, fire and go somewhere. And so how far it goes depends on how far back they pull their little bow. Well, if I were writing a computer program and I wanted to save a lot of processing power, I might say if most people are really only pulling the bow, between, this first x value and this second x value, and that was within my, appropriate amount of error, I might just use the equation of a tangent line instead of using whatever really high-tech, fancy, physics accurate formula would give me the exact flight path, right? I might use something that approximates the right answer. But, if you're sending people to the moon or you're building spaceships or rocket ships and, your tolerance, you look at 0.01, you're like, oh, that's too much tolerance. That's too much error. We're going to have problems. well, then maybe you can't get away with making a linear approximation to save yourself some computational power, right? You're just going to have to do the whole thing, or use a different sort of approximation of some sort. But yeah, these are linear approximations. They're super cool. You're just using the equation, in this case of a tangent line, to approximate the values of a particular particular function that maybe is just really hard to evaluate on its own. So you just create the tangent line and you use that instead. That's pretty much it. So, yeah, I don't think there's anything else that I need to mention in this video. So we're gonna call it here. That's linear approximations. Hopefully the intuition makes sense. The application of it makes sense. And yeah, that's it. This is the last video for this week. We're just going to focus on these two applications. And then next week, we're going to go on into the next most popular application, which is, of course, using calculus to graph functions and do things like that. So super exciting stuff. And I'll see you there later.